All right, guys, so we're moving on to kind of Monero in the future here. So we've talked about the protocol under the hood. Now Adam's going to kind of talk about some, theoretical potential futures for Monero in terms of whether or not it is quantum resistant, whether or not it needs to become quantum resistant, and whether or not I guess that's even possible. So go ahead, take it away.
Cool. Well, thank you for having me. So my talk is, of course, on Monero Post-Quantum. That's the title, and it's going to be mainly 3 parts. The first part is just going to be an introduction to a couple of concepts, including quantum computing and post-quantum cryptography. And then I'm going to go into the Monero Quantum audit a little bit, which was done in 2020, 2021, it was a while ago. So there might be little things that might have changed since then, but I think for the most part, the basic concepts are the same. So there are a few little things in it that are maybe a little applicable today, but most of the stuff is like, looking either like far ahead in the future, just like even currently, if such a thing like quantum computing existed now. Anyway, so with that, let's get into it. Okay, so quantum computing. So introduction to this, that's up here is a wave function. You have basically like a particle beam, and then you have slits, then you have either observed, not observed. And so with the difference between classical computing and quantum computing is, of course, you have classical bits, which could be either 0 or 1, and then you have qubits, which could be in a superposition of multiple states. And so there's qubits, there's qtrits, back when I was reading textbooks on it, which was only 3 years ago, they were all about like, oh, qtrits and qubits are the same. But lately, there's actually been some theoretical, discoveries made that could actually show that qtrits might actually be more viable than qubits. But anything a classical computer can do, a quantum computer can do, plus a little bit more. They're faster for certain applications is the main thing. Intense parallelism. Basically, you have qubits. The main thing is you can entangle them, and then you can just do these like really insane operations, which you do an operation on one qubit, and then it affects all the other ones instantaneously. So that's incredible. It violates what's called a strong Church-Turing hypothesis. And of course, it can generate non-deterministic randomness, which is useful. Next slide. If computers you build are quantum, then spies everywhere will all want them. Our codes will all fail, and they'll read our email till we get crypto that's quantum and dantum. Jennifer and Peter Shor. It's a poem in one of the quantum computing textbooks I read. Peter Shor is a person who, if you know anything about quantum computing, you've probably heard the magical thing they can do is Shor's algorithm, which is Shor's factoring algorithm, which is basically the hidden subgroup problem is, it's a generalized thing, and solving the discrete log problem is one of the the bases of Shor's factoring algorithm. And of course, solving the discrete log problem Monero relies on elliptic curve cryptography protocols, and that would be able to be solved in polynomial time, so really quickly, and so that basically destroys a lot of secrecy. But anyways, that's getting ahead of myself in this talk. The next thing is Grover's search algorithm. Grover's search algorithm these all basically go from like either like most of the algorithms in quantum computing either go from either using a quantum Fourier transform, which can be made a lot faster, or using a search algorithm. And so Grover's algorithm is basically a needle in a haystack type of deal, where you basically have like one value. Let's say you're trying to find like a nonce for a Bitcoin block, and so you go through all the different possible nonces, and you could do this, usually it would take n/2 on average tries, or you get really lucky. The RNG is in your favor, and you just randomly get it the first try. But with Grover's algorithm, you basically just have all the entries kind of in superposition, and you do some amplitude trickery, and then you get eventually the value in square root of quadratic time instead. And then there's, of course, the other algorithms, such as the Bernstein-Vazirani algorithm, Simon's algorithm, and many more. There's the random access oracle algorithm, which there's not much info on that, but that has some really interesting implications that haven't really been very explored. But the Bernstein-Vazirani algorithm is interesting because it's like you can set up a system of linear equations with a quantum computer, solve them classically, and you can reduce crazy stuff like reverse block ciphers and stuff, which could be useful for like finding preimages of hash functions. And anyway, so next slide. So new vulnerabilities. So really getting into it, how powerful are quantum computers? How fancy are they? How fancy are these fancy computers? Well, for Shores, you can see right here, we have like, normal, trying to find, this is like several ages of the universe to find, someone's private key. And here it's like basically like 10 seconds. So really fast. And how many qubits do you need for this? So in the technical paper we wrote, I did an implementation of Shor's algorithm, and I described in the appendix of it some implementation of Shor's algorithm that could be used for solving elliptic curves. And it's something like 512 qubits, potentially, if they're non-noisy. It could range from anything from like 512 to like 10,000. But anyway, so the compute time for discrete logs can go down from like 10,000 years to seconds, depending on, a couple of different factors. And then for Grovers, there's a couple of theoretical hurdles with being able to do this, which I won't get into, but theoretically, if you had an ant miner that was using Grovers to search through possible nonce values, you could mine a Bitcoin block every nanosecond, which would be pretty crazy. But there's other technical hurdles, such as you probably would not be able to get a clock time that fast with a quantum computer because it uses microwave relay stuff. If you really want to get into the actual technical aspects of how quantum computers work, I'm happy to answer a couple questions. And so differential cryptanalysis is the last thing, and that also not included here, as well as random access oracle, which is something quantum random. I don't remember the name, but getting into a bit more technical stuff. And this can be used to do differential cryptanalysis, and there's an exponential speed up with that. So you're either getting quadratic or exponential speed ups, and so with exponential speed ups, you usually get some very game-breaking stuff. But with like quadratic, it's more of just like make things a little bit more simple, and you can actually use conjunction of Grovers and the quadratic speed up in conjunction with the exponential speed up, and that adds a bit more things that can be explored in terms of vulnerabilities introduced. Right, next slide. Okay, so our savior, post-quantum cryptography. There's a couple different fields right now, and there's more. All this is a very rapidly advancing field. Within the 3 years since I've been directly involved in it, it's quantum computing and post-quantum cryptography have just been in this crazy arms race. And there's actually been lattice-based protocols that have been introduced that like later 2 years, someone was like, you can use a quantum computer to break that lattice-based protocol. But for the most part, lattice-based problems are PQ hard and assumed to be BQP as well. Or, sorry, NP hard. Yeah, sorry, I'm forgetting my complexity classes. So then you have supersingular elliptic curve isogeny based, which is also actually, so these would probably be some of the two most likely candidates if you wanted to switch to like some post-quantum Monero protocol. And then there's multivariate based, but actually recently there's a paper exposing the multivariate might be a little, so this is like basically just using lattices. This is lattice based, finding a point on a lattice. Supersingular elliptic curve isogeny based. This is the equation for finding points on an elliptic curve. Isogeny is essentially, and then multivariate, like you have a chaotic system and you, some stuff with that, and then hash based. And there's actually a Bitcoin, similar to Bitcoin, a cryptocurrency protocol that uses a hash based already, which is quantum resistant, which is an extended Merkle signature scheme, which is basically you have a Merkle tree, and then you basically can verify a signature that way, and you can build an entire blockchain network that way and still have traded crypto tokens that way. And then of course there's quantum-based cryptography, which is way far in the future, which is using quantum computers themselves as nodes in a blockchain network, which would be pretty interesting. So with BB84, for instance, you basically have completely, unless you want to try to violate the laws of physics or break quantum mechanics in some way, it's completely secure cryptography. Anyways, so next slide. All right, so this is probably a little bit of the work we did. This is, I wish maybe up a little bit more, but as you can see, that we basically, what we did was we looked at like the different features in Monero. I don't know if Triptych, it should have it down there, but I don't know if that was finished since then, but we looked at that as well. But we looked at a couple of different aspects of the mechanisms that we were like, okay, well, if you did like Shores on it, or like, discrete log, stuff, magic with quantum fancy computers that, break things, yes, in a lot of cases. That's the main thing that breaks things. Grover's algorithm, you can use conjunction of Shores and Grover's to actually do some, mainly it provides a lot of things we found out along with Fourier fishing. And then quantum access to random oracles is also a pretty yeah, that also provides some problems as well. But as you can see, the main thing is Shor's. Everything else, actually, the proof of work mechanism is surprisingly resistant. So that thing where I was saying how like an ant miner with rovers would be able to just mine Bitcoin every nanosecond wouldn't be the case for Monero. So it's a little bit more secure than other cryptocurrencies in the event of quantum apocalypse or whatever. Anyway, so next slide. Yeah, so as well, I shouldn't say urgent because it's probably a bit more further in the future, but obviously out of all the things, of course, the main thing is it's possible to extract private wallet keys from on-chain data. So a couple of other things though, is that something would possibly be able to do: violate signer ambiguity, breaking binding Peterson commitments, breaking bulletproof range proofs, colliding transaction identifiers. But it basically breaks a lot of stuff. A lot of it, some of it actually relies on this thing that I was saying earlier, quantum access to random oracles, forged Schnorr snakes. The thing with that is there's not a lot of papers on quantum access to random oracles, but it seems that it is a possibility that could be leveraged. So yeah, to be continued. Proof of work surprisingly secure, as I said. Cache shock resistant Grovers and quantum differential cryptanalysis. So it's a good hash function to use. Proof of work surprisingly secure. And in the case of this happening where everything's on fire, it still would be probably a better thing to hedge your bets on than most other cryptocurrencies. Or even bank account info and banks. Wells Fargo probably would not be the best bet to put money into in this case. But, okay, next slide. Oh, yeah, there it is a little bit. So yeah, how feasible are post-quantum alternatives right now? Well, 2 years ago in this case, because that's when this table was made. Surprisingly, they're not that bad in some cases. They're still, you couldn't build an entire network off of them at these things, but honestly, these numbers have gone down and certain things have gone up. So as you can see right here, like for Monero, SIG proof size is like, at least when this was done, this was like 0.25 kilobytes, but then you have like Ring Rainbow. By the way, Ring Rainbow actually in a very recent paper like 3 months ago supposedly has this is a multivariate scheme. It has like very horrible flaws and it might have to be fixed. And then we have the public key size. This is very big, but then you got some smaller ones down here and up there. Raptor 512 is a lattice-based one. Generation time is feasible. You have the verify time is also pretty feasible for Raptor 512. Yeah, so things, it's not as impossible as you might think. Maybe wait a little while, but this is written 2 years ago, and already things are much more, feasible in terms of that. Anyways, next slide. So, summary of the audit. Current Monero protocol is highly vulnerable to known quantum algorithms, mainly Shor's, which is, kind of what we expected going into this. The main thing which is a little iffy, is like possible retroactive de-anonymization, which is probably something to think about. Like, okay, let's say you bought jelly beans from Steve 10 years ago, and the government really doesn't like that, or something. And then if Jeff Bezos happens to have a quantum computer in his secret underground volcano lair or something, and he finds out that you sold those jelly beans to Steve, and he's like, oh no. I don't know, so that's something to consider. So potentially low-hanging fruit that can be fixed easily now. But anyway, so possible retroactive de-anonymization relies upon quantum access to random oracles, which is still a little iffy to some degree, but it's still a possibility. So some potentially low-hanging fruit that can be fixed easily now. Quantum-resistant range proofs, potentially. Yeah, we could make some range proofs that might be a little bit easy to fix. Switch commitments, and then restrict blinders. These might be actually interchangeable. I didn't really look into that too deeply when I made this slide. And then stick to using one-time private keys, of course, is a given if you already haven't been doing that. But if you weren't using one-time private keys, I think it might, like a while ago, that might be a bit more vulnerable, like to retroactive de-anonymization. But yeah, I think in any case, you probably should just be doing that anyways, if possible. Anyways, next slide. All right, the fun part, speculations. Currently a blockchain, so yeah, quantum resistant ledger is a blockchain protocol which currently uses XMSS hash-based cryptography. So it's quantum resistant, and it's around. So even if it turns out someone had a quantum computer today or tomorrow or yesterday, there still would be a blockchain available right now. a lot of people, and I'm sure more post-quantum projects will probably spring up as time goes on. But there is one in any case. Then there's noisy intermediate scale hardware. IBM has stated 120 qubits machine sometime by like next year, I believe, if they haven't already done that. And they've made a roadmap before the end of the decade to have 1,000 qubits, which is like pretty surprising to have that like publicly available. And like I said, 512 is basically at the point where potentially you could use shorts to break discrete log cryptography. Or hidden subgroup problem, potentially. We're looking at like 512 to like 10,000 qubits is kind of within the range of that. And then using qubits is a whole other game. And so quantum advantages are being utilized on a commercial scale using noisy intermediate scale hardware. So this is basically, we're just seeing like basic commercial applications, combinatorial optimizations. It's a little bit more efficient to run certain programs on quantum computers than classical computers, commercially speaking. So it costs more money to run it on a supercomputer than to run it on a quantum computer in a few small cases. So it is finding some industrial applications, which is really interesting, like right now. More examples of quantum supremacy are demonstrated by experimental hardware like every year. So this is like stuff that a classical computer couldn't do in 10,000 years, sort of a deal. And different examples keep on, but nothing too extreme in my knowledge, at least yet, that's publicly available at least. And then new post-quantum crypto is constantly being developed. Key size and compute times continue to go down. Post-quantum crypto is, of course, in an arms race with, quantum computing, and so it's kind of back and forth. But yeah, a lot more protocols are being built off of it as well. And you could probably do atomic swaps with lattice-based cryptography at some point too. I don't know. Timeline: quantum computing threat ranges anywhere from 3 years to 3 decades, I would assume. Since capabilities are known, at some point, if you're using, not post-quantum cryptography, you should probably switch at some point. And I mean, if we really want to look at the end game of this, not just for Monero, but like any other cryptographic protocol, you should probably implement a blockchain that uses it at some point, hard fork or something, I don't know. Long-term, what would a quantum cryptography blockchain even look like? And by that, I mean, if you use basically the same thing of decentralized consensus, where each node is a quantum computer, and each quantum computer is basically sending communications to each other, and they're using like basically qubits or qubits, which have like basically completely foolproof cryptography, and you can do a bunch of really other fancy stuff as well. Like, take for a moment just to like imagine that world. Like, it's really interesting to think about. Like the quantum internet. It's a real thing that could potentially happen within our lifetimes, which is interesting. Next slide. There we go, conclusions. So quantum mechanics could be wrong. Quantum computers might all be a hype pipe dream. Most likely the threat is real. We're in a grace period right now where we know the capabilities of quantum hardware and have time to switch to node-resistant cryptography. For continued secrecy and safeguarding, there could be a black swan event in which, tomorrow, suddenly the internet's gone, like that in a very extreme example. And there could also just be examples where it's just like, we find out that like, some stuff is no longer secret. But you can't really predict that. I mean, you can try to make predictions, 3 years from now, 10 years from now, 3 decades from now, not in our lifetimes, And then like, really, if you really want to look at it, like I'm gonna, for a second here, get really skeptical about all this. Okay, what if it's just all just like, bullshit, and like you can't even like there's like there's two main things, actually 3 main things. Strong Church-Turing hypothesis violations is kind of like, this seems to violate a very fundamental law of computer science to some degree. But I mean the strong Church-Turing hypothesis. The second thing is it could be that capability is solid state physics. That there could be technical hurdles in solid state physics that are just like really it turns out that it's actually a lot harder to do certain things than not. And that's why I'm saying if it's publicly available, it's found out that 120 qubits are easily possible, non-noisy qubits, then it's kind of like that's a big technical hurdle that it's going to grow exponentially from there. But there could be things with that. And then lastly, there could be just like really ridiculous. Quantum mechanics could just be a completely flawed theory. It could be break down at certain points that we don't know about yet. I mean, physics it is one of the most tested theories within our knowledge of over 100 years. But I mean, some people are like, maybe if you have enough like qubits in a room, in a box, in a computer, put them all together and it collapses into a black hole, which is a possibility given information theory. And so, imagine for a second what like if it would be real though, like, barring these possibilities. Everything else is kind of held up to skepticism. The fact that we're using it for commercial applications right now, my money is on that it's going to develop further because people are making money off of it. So anyways, it would be really disastrous if it just, Shor's algorithm capable quantum computer came out. Okay, last slide. There we go, acknowledgements and references. Big thanks to Monero Talk Show for hosting me. Huge thanks for Mitchell right there, Isthmus for running the project, for Monero Post-Quantum and getting me involved in it, as well as Brandon G. Goodell for his large contribution to the project. There was necessary help with technical details. Thanks to Insight Data Science for providing necessary organizational resources and providing wonderful opportunities. And personal thanks to everyone who helped me on this project, including friends and family. And lastly, massive big thanks to you, the community, who provided wonderful input and support for this project. Thank you. Oh, and then I have one more slide with references if you're curious for what I've been saying, so I'm not talking out of my ass. There you go. I think one of these things, if you really want to look at the technical implementation of 512 qubits for breaking elliptic curve cryptography, I think it's one of these here. I'm not entirely sure which one. No, it's not that one. I don't know. You can look through all those references. Oh, a question already. Someone needs to pass him a mic. I mean, you could also yell really loudly. I could send you slides, yeah. Also, these aren't all the references I'm talking about either. Yeah. I can send that too, yeah. Well, yeah. Yeah, I guess I'll open up this to questions. Anyone have any questions? Yeah, oh, that guy. Physics and astrophysics from UC Berkeley. Yeah, I took some of the first quantum computing classes there. So I have I double majored in astrophysics as well. And then I got involved in this project. I mean, I probably should have told it from like the storyline perspective of hearing about the talk. I basically did a project on, Grover's algorithm to, potentially mine a theoretical small version of Bitcoin, and then kind of grew from that. And they're like, oh, wow, this is actually real. You can literally go to the IBM Quantum Experience and just run open source hardware on your own for fun with 5 qubits. All the cool kids are doing it. Any other questions? Once, twice, thrice. All right, well, I'll be available for a little bit for questions if anyone's interested. Who's next? Sure. I don't know how fast that was.